The National Map is a collection of mapping products and services produced by the USGS National Geospatial Program. The products and services are accessed via the Internet through service calls and graphical user interfaces. The National Geospatial Program has released a series of how-to videos for people who are working with the National Map data and services. The videos show how to use the services and interfaces to access data and tools for viewing, analyzing, and printing geospatial data. The training materials are a mixture of video and PowerPoint-based lessons. Lessons 1 and 2 serve as an introduction to the training materials. The remaining lessons are designed as quick how-tos and may be viewed as needed in any order depending on the user. Any use of trade, product, or firm names is for descriptive purposes only and does not imply endorsement by the U.S. government. Lesson 10C3, Clipping LAS Data and Creating Derivative Products in Global Mapper. Lesson 10C1 and 10C2 introduce the basics of interacting with LiDAR point cloud data in Global Mapper. This lesson will cover cropping LAS files and generating derivative data in Global Mapper. If necessary, please review Lesson 10C1 for guidance with importing LAS files, filtering and visualizing LiDAR point clouds in Global Mapper. By the end of this lesson, you will be able to load multiple LAS files, define and use polygon area of interest to subset LAS files, and generate and export raster surfaces and contours derived from the LiDAR point cloud. In this tutorial, we are using uncompressed LAS data, but the National Map also offers compressed LAS data, which is compatible with Global Mapper as well. If you're interested in learning more about using USGS LiDAR data in other software packages, additional videos show how to use the LiDAR data in ArcGIS Pro and LP360. For this lesson, we will be using the same 6 tiles of LAS data from Lesson 10C1. If you have not done so already, please download the USGS LPC CO So Platte River data for lessons.zip file from the FTP site at rockyftp.cr.usgs.gov/training_data. After you've downloaded the LiDAR data, extract the zip file into a folder on your local computer to use during this lesson. The National Map has a download client where you can find USGS products, including elevation data such as LiDAR point clouds, at viewer.nationalmap.gov/basic. If you are interested in learning more about downloading products on the National Map, be sure to check out our training videos located at www.usgs.gov/ngp videos. This exercise specifically uses Global Mapper version 20 with the LiDAR module installed. However, any version that is 18 or newer should suffice for this tutorial. Launch Global Mapper. Make sure that your LiDAR license is active before proceeding. Under the Help menu, click on License Manager. In the next screen, make sure the LiDAR module is toggled on, then click OK. Note that Global Mapper preserves settings from previous use sessions, so the defaults in your interface may differ slightly from what is shown in this tutorial. From the splash page, select Open Data Files. In the Open window, browse to the location of the LiDAR point cloud LAS files that were downloaded from the FTP site. Select all 6 original LAS tiles and click Open. We will load the LAS tiles in their entirety. Therefore, when the LiDAR Load Options window appears, make sure all the point data are loaded by clicking the Select All button for point classifications and return types. In the bottom left corner, toggle on the option to use these options for all LiDAR files in the current group, then click OK. Each of the 6 tiles will be loaded using the same settings. This may take a minute to process. When the LiDAR data load in the View window, make sure all classes are enabled. To do this, click the Filter LiDAR Data button, then select Enable All and click OK. By default in the 2D View window, the LAS tiles are displayed with a color LiDAR by elevation symbology in an Atlas shader color palette, where blue corresponds to the lowest elevation and red corresponds to the highest elevation values. Because Global Mapper preserves settings from prior sessions, if you've previously altered the symbology selections, your display may appear differently. If needed, use the drop-down menus to display the LAS tile with the settings seen here. When working with many large LAS tiles, it is sometimes helpful to clip point cloud data to a specific area of interest to save processing time and storage space. Global Mapper uses polygon features to define the area of data to clip. The polygon feature can be an existing shapefile, such as a building footprint, or the polygon can be created directly in the Global Mapper 2D window. We will use the Digitizer Create toolbar to create an area of interest polygon in Global Mapper. If the Digitizer Create toolbar is not present on your screen, turn it on by selecting the View menu, then click Toolbars. Active toolbars have a checkmark next to them. If needed, toggle on the Digitizer Create toolbar now. We will be creating an area of interest that omits the foothills on the west part of the tile. On the Digitizer Create toolbar, click Create Area Feature. Now left-click to create vertices and draw a polygon that encompasses the area of interest and avoids the foothills. Right-click to finish drawing the new area feature. A Modify Feature Info window pops up to allow you to define a name for the feature, specify style, attributes, and the feature layer to save the polygon to. In the name field, type AOI for area of interest. Under the Feature Layer dropdown, select User Created Features. Accept the default options for style and attributes and click OK. You will now see a new user-created feature layer appear in the Control Center, and the polygon labeled with AOI appears in the 2D window. To clip the last tiles loaded into the 2D window, we must first select the polygon or polygons that will define the clipping boundary. We only have one polygon to select, however. These selection options can be used to select multiple polygons as well. You can use the Digitizer tool to select one polygon at a time by clicking on each feature. Or you can select all polygons within one or more layers from the Control Center. Right-click on the user-created feature layer and click the Select option to select all features within the layer. This will select our newly created polygon. With the newly created polygon selected, right-click in the 2D window and select Crop Combine Split Functions, then Crop. In the Crop to Selected Areas Setup window, use the Layer Feature drop-down to select Create New Layer for Feature. Accept the remaining defaults and click OK. When the Enter Layer Name prompt appears, type Clipped Last Tiles and click OK. The Layer Projection window that pops up allows you to define the projection information for the newly clipped layer. This window automatically reflects the current projection of the workspace. We will use this default. Click OK. After a few seconds, the new layer is added to the 2D display and Control Center. To view the new layer, turn off all layers by clicking on the check mark next to Current Workspace, then turn on the Clipped Last Tiles layer. This new layer can now be used as an input last file to any LiDAR processing function. Note that this layer is only saved in the memory of the current Global Mapper session. To save the newly created layer to an external file, right-click on the tile name in the Control Center. Select Layer, then click Export. Select LiDAR Last File as the export format and click OK. A tooltip pops up to inform you that the last file will be exported with the current display projection. This will export the last tile using the current horizontal projection, but will not save a vertical projection. Click OK. In the LiDAR Last LAS Export Options window, click on the Vertical Coordinate System dropdown and select NAV88 to match the input data. Accept the remaining default options and click OK. Now navigate to where you saved the training data last tiles and save this exported tile as lesson 10C3_clipped_last.last. This may take a few seconds to export. The newly clipped LiDAR layer is now saved as a last file. You can now perform any LiDAR visualization, classification, and processing on just the data contained within your area of interest, using the same workflow as you would for a single LiDAR tile. Global Mapper provides the ability to create and export elevation grids and contours derived from the point cloud. You could create a derivative product from a clipped last, such as the lesson 10C3_clipped last file that we just created. Or you can create a derivative product from all loaded last tiles. We will use all 6 last tiles to create derivative products. Turn on all layers by clicking the current workspace toggle, and then turn off the user-created features and the clipped last tiles layers in the Control Center. We'll start by creating a digital elevation model, or DEM. Click the Create Elevation Grid button on the Analysis toolbar. This tool generates gridded elevation surfaces from input vector features. In this case, we will use the LiDAR point cloud as the input. Next, make sure all 6 last tiles are selected in the Selected Layers window. Click OK. In the description box, type DEM. The vertical units are detected from the input dataset and as such are in meters. However, you can change them to feet if you desire the output grid to be in feet. The grid method defines how vector values will be used to generate the output grid. The default is triangulation, which creates a triangulated irregular network using the LiDAR points. The binning methods create a raster output by overlaying a regular grid and calculating the minimum, maximum, or average within each bin. We are interested in a bare earth DEM, so select Binning Minimum Value DTM from the drop-down menu. The grid type drop-down specifies the values used to calculate the grid. We will use the default elevation values, however, this drop-down provides additional options such as intensity values, height above ground, and others. Any LiDAR filters applied in the view window will carry over to this tool. You can also define the points used through the Filter LiDAR Points to use by Elevation Class Color button directly in the tool interface. Click the Filter LiDAR Points to use by Elevation, Class, Color, etc. button. In the Filter LiDAR Points window, select Clear All and then select Class 2 Ground and click OK. The grid calculation will now only refer to ground points when creating an output. The grid spacing option defaults to automatically detect spacing based on the point spacing of the input dataset. In this instance, the automatic spacing multiple of point spacing is set to 5. Optionally, you can also set the grid spacing to a desired resolution using the Manually Specify the Grid Spacing to Use option. If you choose this option in the future, make sure the grid spacing is not less than the point spacing of the LiDAR data. We will accept the default automatic option. This tool uses interpolation to fill any gaps from the input dataset in the Elevation Grid No Data Distance Criteria setting. The grid tightness slider allows you to specify how loose or tight to make the interpolation. Loose settings enable the interpolation to fill areas with no data values, whereas tight settings leave no data holes in the DEM. We will use a value around 25 so the DEM output is continuous where buildings exist. Accept the remaining grid options defaults. The Tiling tab provides the user options to split up the data on an export. We want to output our results as a single tile, so keep the No Tiling, Just One Export File option selected. The Grid Bounds tab provides several options to subset the dataset for the grid creation. We will accept the default to use all loaded data. Now click OK. This will quickly calculate an output layer stored in the workspace memory. This raster is a bare earth layer derived from the ground points of the LiDAR point cloud. We can repeat the process to create a digital surface model, which will also contain above ground objects such as buildings and vegetation. Again, click on the Create Elevation Grid button, make sure all 6 last tiles are selected in the Selected Layers window, and click OK. In the description box, type DSM. Now change the grid method to Binning Maximum Value DSM. Click on the Filter LiDAR Points to use by Elevation, Class, Color button to define the points to use. To create a surface model, we want to use above ground points while excluding all possible noise points. If you recall from Lesson 10C2, these last tiles contain noise as well as misclassified noise points due to changes in last versions. Therefore, in the Filter LiDAR Points window, unclick Class 7 Low Point Noise, Class 11 Road, and Class 18 High Point Noise. The tool remembers the remaining settings from the previous run, so click OK to generate the DSM raster layer. Once the DSM layer generation is complete, click the Full View Home button to center the layers, then click the Image Swipe button to compare the generated raster layers. This allows the user to swipe the top layer out of the way to view the layer underneath. Click OK to close the tooltip. In the Select Layer to Swipe menu, select DSM since that layer is currently on top in the 2D view window. Then click OK. Now click and hold the left mouse button on the edge of the tile and drag the cursor towards the center. You can see the DSM layer containing the trees and buildings pull back to reveal the underlying bare earth DEM below. You can perform this image swipe from any side to visually compare the two layers. To get a more detailed comparison of the DSM and DEM, zoom into an area with buildings and perform the image swipe again. Global Mapper can also use these derived raster layers to generate contours. We want our contours to be based on the bare earth surface and not the above ground features. So in the Control Center pane, deselect all layers, then select the DEM layer. Click on the Create Contours button on the Analysis toolbar. The Contour Generation Options window enables users to define the contour generation parameters. We will create contours with 5-meter intervals. These intervals will have minor contours every 5 meters and major contours every 10 meters. The elevation, range, and resolution options are detected from the input dataset. For most contour generation, it's suitable to accept the defaults for these fields. Many additional options exist within the tool to constrain contour generation parameters, define the tiling scheme, and spatial extent of contours. But for our purposes, we can leave them unaltered. Click OK to create the contours. A new vector line layer will be generated within the Global Mapper workspace. The generated contours will be superimposed with labels on top of the DEM surface created earlier. All layers we created are stored within the Global Mapper workspace, but are not saved as an external file. To save files, use the same steps performed earlier to export the clipped last tile. The Export menu is accessed by right-clicking on an active layer, selecting Layer, then Export. From there, you can select an appropriate file format and export parameters, and then save the file to a folder of your choosing. This concludes Lesson 10C3, Clipping Last Data and Creating Derivative Products in Global Mapper. In this lesson, we discussed how to load multiple last tiles, use polygon features to clip last files, and generate and export derivative raster surfaces and contours. If you are interested in learning more about using LiDAR data, please see the additional USGS LiDAR training videos in ArcGIS Pro, LP360, and Global Mapper at usgs.gov/ngp videos.